But those two things, I think, are the most useful.
Okay.
Yeah.
All right. Cool. I did not realize that we got all of these. I thought it was just going to like a few. It's kind of a lot.
It's a lot, but it's not so many for like test one. I mean, the formula sheet on the test covers all the entire semester.
Yeah, that's what I saw.
Yeah. So it's just one. Yeah, it covers the whole semester.
All right, cool.
Okay, I'll get started. Wanted to begin with a reminder again that next Thursday, 1 week from this moment, is test number 1. Test number 1 has 3 problems on it that you will work out in detail, numerical problems. It has 10 true-false questions on it that are conceptual, like lecture quizzes. 80% of your score on the test is from the problems that you fully work out, and 20% is from the true-false questions. It's covering all the material in the 9 lectures from the very first lecture up to the lecture next Tuesday prior to the test. Any questions on all that? Okay, then I'll move on with the class. So today's class, I want to carry on with our work on electrical circuits. We began it a couple of classes ago, and we'll continue it to next Tuesday's class. Specifically, in today's class, I want to talk about these topics. I want to talk a little bit about batteries, what batteries are, what batteries do, and specifically EMF, electromotive force of batteries. I want to talk about resistors. I want to talk about arrangements of resistors. We're going to talk about series arrangements of resistors. We're going to talk about parallel arrangements of resistors. You might want to remember that we talked about series arrangement of capacitors and parallel arrangement of capacitors. Then finally, I want to talk about, or start talking about, more complicated circuits where the resistors are in series and parallel, and how we solve those more complicated circuits. This is going to be a story, a problem that will carry on from today's class into next Tuesday's class, where we'll learn some more methods, some more techniques for solving complicated circuits involving resistors and batteries. So this is the plan. Okay. So this slide is to give you an idea of the questions, the problems that we'd like to answer with the electrical circuits in this class and also in the next class. If you want to think of an electrical circuit, you might want to think about the electrical circuit in your home. In your home there's an electrical circuit, and in that circuit the incoming electrical current to your home, the incoming electrical power to your home, is delivered and shared over a wide range of different components. So it's shared to the lights in your home, it's shared to the heating in your home. The stove gets some of the electrical power and the electrical current. The washing machine, the dryer, wherever they are in my house, I don't know, but they get some of the electrical current and electrical power. So that's an example. A household circuit is an example of an electrical circuit, and it's an example of sharing out the supplied electrical power, the supplied electrical current to the components. And that's an example of the sort of things that we're going to learn how to figure out, learn how to solve in today's class and the next class. So here's a circuit, and we're going to learn how to figure out the electrical current through the components of the circuit, the electrical potentials across the components of the circuit, and the electrical power that's distributed to the components of the circuit. Those are the basic circuit questions. So let's get on with my bullet point list of things we're going to do today, which starts with batteries. What are batteries? On this slide, I tried to give you an analogy to an electric battery by showing you a different type of battery. No, I'm not showing you yet. I'm going to show you a gravity battery or a water battery. So let's start with the water battery that's depicted in this little sketch here. See if we can understand what the water battery does in this little picture, and then we'll draw the water battery's analogy with a regular electrical battery in an electrical circuit. So this water battery, the purpose of this water battery is to raise water to a greater elevation. It's raising water to a greater gravitational potential energy. And so if you look at this arrangement, there's a pond or a lake or a whatever down here of water. There's this arrangement, sort of, might call it a contraption. It's got a bunch of buckets that are tied together. Look at all this, there must be 50 buckets here. And they're all tied together, and as this wheel is turned by this person, then these buckets come up on the left-hand side carrying water, and they go over the top here, and they deposit the water into this trough here. And so this machine, this water battery, is, when we power it with the chemical energy in this human, this machine is raising water from lower gravitational potential energy to higher gravitational potential energy. We could define an electromotive force for this machine. It would be, if we were to define it, we would define it as the change in gravitational potential energy as we raise the water, as we raise the mass of water, divided by the mass of water. So this would be an electromotive force that we would define for this machine, and I'm defining this equation because it's analogous to the electromotive force that we define for a battery. So this is exactly what a battery does. A battery doesn't look like this inside, obviously, and a battery isn't raising water to a higher gravitational potential energy, masses of water to a higher gravitational potential energy, but a battery, an electric battery, is raising electrons, is raising charge to a higher electrical potential energy. And we define an electromotive force for an electrical battery as the change in electrical potential energy, when we raise the charge, we raise the electrons, divided by the amount of charge that we raised. And so this is analogous to a battery in an electrical circuit. We should be thinking of this down here as not water, but as electrons that these buckets are carrying up. And they're carrying the electrons up to higher electrical potential energy rather than higher gravitational potential energy. We should imagine, right, this machine is operated by a person who had to have lunch, had to be provided chemical energy. The battery, an electrical battery, is operated not by a person, but by chemical energy again. It had to use up its lunch to raise the electrons to higher electrical potential energy. In the case of the electrical battery, this quantity that we call EMF, which characterizes the battery, which is the change in potential energy when you raise the electrons up to a higher electrical potential energy divided by, the charge of those electrons. This is called the EMF, and it's actually measured in volts. So it has the units of electrical potential. It is measured in volts. And as you know, when you go to Kroger's, you buy a battery. You're buying a 1.5 volt or a 3 volt or a 9 volt battery. So they sell you different voltages of batteries, different EMFs of batteries. It's a poor choice, yet again, another mistake. A poor choice of a name, electromotive force, because it's not a force. It's not measured in newtons. It's measured in volts. It's a change in energy per unit of charge. So it is a poor choice of name, electromotive force, but it does sort of describe the fact that the battery is going to push the charge, push the current around the circuit. Okay. Here's a couple of sketches of batteries in circuits. The one on the left-hand side is what I would call a kind of a perfect battery or an ideal battery. The one on the right-hand side is what we would call, a real battery, a realistic battery. So over here, this is a circuit involving an ideal battery. This is a circuit involving a real-life battery. And on this slide, I just want to say a few words about the characteristics of an ideal battery and a real-life battery. Often when we solve circuit problems, we imagine we've got an ideal battery. But in practice, if you're working with circuits, you have to remember you've got a real battery, and they are different. So an ideal battery, what's an ideal battery? An ideal battery is one that always supplies the same electromotive force, that thing I gave the symbol epsilon, that quantity that's measured in volts. So an ideal 3-volt battery always supplies 3 volts of EMF, no matter what current you draw from the battery. So if you drew a microamp of current, tiny current from the battery, it would have an EMF, supply an EMF of 3 volts, a voltage of 3 volts. If you drew a milliamp from that battery, so that's 1,000 times more, it would still provide an EMF of 3 volts, a voltage of 3 volts. If you drew an amp, which is a huge amount of current, from that 3-volt battery, the ideal battery would still supply a terminal voltage, an EMF of 3 volts. So an ideal battery is one that no matter how much current you draw, you always have a voltage between its terminals that's the same. For the 3-volt battery, that's 3 volts. A real battery, on the other hand, if you've got a realistic battery, 3-volt battery, and you draw a small current, 3 microamps, you'll see 3 volts across the terminals of the battery. But as you start to turn up the current, maybe we go to drawing 1 milliamp, 1,000th of an amp, so that's a significant current, then we might see that the voltage across the terminals is a little less than 3 volts. Maybe it's 2.9 volts, so it's decreased a little bit. If we try and draw an amp from the 3-volt battery, then we'll discover that the voltage between the terminals of the battery, the EMF, the voltage it's supplying, is much less than 3 volts. So with a real-life battery, if you try and draw a lot of current, you won't get the full terminal voltage. If you try and draw just a little bit of current, then you get almost the full current. This feature of batteries, ideal batteries versus real batteries, I'm going to come back to a problem involving this at the end. But from this moment on, we're going to, most of the time, talk about circuits with ideal batteries, and then we'll look at a problem involving a real battery. Okay, so I want to talk about resistors in series, and then we're going to talk about resistors in parallel. And we're going to try and understand how resistors in series operate, how resistors in parallel operate. Specifically, we're going to understand how resistors in series and parallel operate by introducing the concept of an equivalent resistance. Remember, we introduced the notion of an equivalent capacitance for capacitors in series and parallel. So similar ideas. So on this slide here, you see a circuit on the left-hand side. And this is a series resistor circuit. So it is a complete circuit. It's got a battery downstairs here, and it's got two resistors connected in this way to the battery. And this is what we mean by a series circuit. What we mean is that those two resistors are kind of connected end to end in the circuit. What we mean is that if you're an electron in the circuit and you're going to run round from the negative terminal of the battery to the positive terminal of the battery, as you're repelled from the negative terminal and attracted towards the positive terminal, you're going to have to go through both of these resistors. The only route around the circuit is to travel through both of the resistors. The current in the circuit goes through both of the resistors. That's a series circuit. So this is a sample series circuit, and I labeled the two resistors R1 and R2. Over here, I've drawn another circuit, which is going to be our equivalent circuit. It contains just one resistor. I'm going to call it the equivalent resistor, which the meaning of equivalent resistor just means that if we supply the same voltage to this equivalent resistor as is supplied to this circuit of R1 and R2, this equivalent resistor draws the same current from the battery as this arrangement, R1 and R2, draws from the battery. So that's the meaning of equivalent resistor. What we're going to do is figure out how to find out that equivalent, or I'm going to tell you how to calculate that equivalent resistance, and we're going to use that concept of equivalent resistance to solve problems of resistors in series circuits. Okay, so the key to understanding this series resistor circuit I've written down here. So this is the key. When you look at that circuit, you want to, there's going to be the equations that describe the circuit, but if you want to understand how the circuit is operating, these are the two keys. And the two keys concern the flow of the current in that circuit and the distribution of the battery's voltage in that circuit. So the first important point about a series circuit is that the current through resistor R1, that's the one on the left, is the same as the current through resistor R2, that's the one on the right. You can't lose any current or acquire any current between the two resistors, and that's actually the same as the current that's flowing through the equivalent resistor. So a key to understanding the circuit with the two resistors and its relation to the equivalent resistor circuit is that the same current is flowing through R1, R2, and the equivalent resistor. So that's the understanding about current. Then there's the voltage. The battery is supplying a voltage to these two circuits, the one with R1, R2, and the other one with the equivalent resistor. The understanding of that battery voltage being supplied to R1 and R2 is that R1 and R2 will share that voltage. So one resistor, R1, will get some fraction of it. The other resistor will get the remaining fraction of that voltage. On the other hand, the equivalent resistor in the right-hand circuit, the equivalent circuit, that gets the entire voltage that's supplied by the battery. So that's the understanding of the voltages in the circuit. The battery is supplying a voltage, R1 and R2 will share it. The battery is supplying a voltage in the right-hand circuit, the equivalent resistor gets the entire voltage. So those are keys to this circuit. Based on that, and it's actually just based on that notion, that concept, and Ohm's law, V equals IR, you can figure out the relationship or the formula, the equation for the equivalent resistance in terms of the individual resistances. So I'm not writing how I figured it out on here, but it is quite straightforward. It just uses Ohm's law. The equivalent resistor for these two resistors in series is just the sum of their two resistances. It's as simple as that. And actually, in general, supposing you had three resistors, R1, R2, R3 in series, just sum those up. If you had four resistors, R1, 2, 3, and 4, just sum those four resistors up. That's the equivalent resistance of a series circuit of resistors. You just sum the resistors. There's an important point about that. When you put resistors in series like this, you're making a larger resistance. The equivalent resistance is larger. It's important because that makes a lot of sense, right? When the current has to flow through R1 and then flow through R2, well, R1 is some sort of resistance to the current flow. R2 is an additional resistance to the current flow. So we would expect the equivalent resistor to have more resistance to the current flow than individually R1 and R2. And it does. It has the summed resistance of R1 and R2. So that's the rule for equivalent resistors. For series resistors. Let's look at an example. Just to get an idea, let's look at an example. I got a little problem here. In this problem, we've got an arrangement of two resistors in series, and a circuit is completed with a battery. We're told that the battery supplies 6 volts to the two resistors. The resistor that I called R1 on the left is 2 ohms. The resistor I called R2 on the right is 4 ohms. And what we've got to do is figure out a whole bunch of things here, actually. We've got to figure out the current through the two resistors. We've got to figure out the potentials across the two resistors. We've got to figure out the power that is being dissipated in the two resistors. So there's actually 6 quantities I'm going to figure out. It sounds like it might take a while, but actually, if we go about it the right way, it doesn't take too long for this 2 resistor circuit. So we're going to go ahead and do that. So let me see. I think I'll do this on this thing. And on this thing, I've drawn on the left-hand side, the circuit we were told in the problem with the 2 resistors and the battery. And I've labeled it with the resistances of the 2 resistors, the 2 ohms and the 4 ohms, and the voltage supplied by the battery. We're thinking of this as an ideal battery. I've also added, because it's going to help me solve this problem, I've added the equivalent circuit involving a single equivalent resistor that for the same voltage draws the same power. And I also added the value of that equivalent resistance. It was easy for me to calculate that. I just got to add R1 and R2, 2 and 4. That gives me 6. The equivalent resistor is 6 ohms. It resists more the current flow than the 2 individual resistors. So I've already done a little calculation here, a little sort of warm-up where I calculated the equivalent resistance. We've got to figure out the current. I'll call this part A, the current through the 2 resistors. So so this is R1, this is R2, this is R equivalent. The current through R1, which I'll label I1, is the same as the current through the second resistor, the one on the right, I2, is the same as the current through the equivalent resistor. This was a key to how this circuit operates. So I'm going to use that key, and this is actually the golden key in solving this problem, that these three currents through the two individual resistors and the equivalent resistor are the same. It's a golden key because I can figure out the current through the equivalent resistor using Ohm's law. Using Ohm's law, V equals IR. If I want the current, I've just got to divide V by R, the equivalent resistor's resistance. And I know that the battery is supplying 6 volts to it. I know that the resistance of that resistor is 6 ohms. And so that current is 1 amp. And that's the current through the circuit on the right with the equivalent resistor, and it's the current through the two resistors on the left-hand circuit, R1 and R2. So in that one moment, I've solved the current through all these different components. We then want, what was the second part of the question? Second part of the question is, what is the voltage across R1? What is the voltage across R2? That's a question about how the voltage is shared out. We said that's another key to the circuit, that those two guys, R1, R2, are going to share the voltage from the battery. Once you know the current through them, then you can use Ohm's law, V equals IR, for each of the individual batteries, just to figure out the voltages across them. So I've just got to multiply the current through I1, that's 1 amp, by the resistance of R1, that was 2 ohms. And if I do that, that's 2 volts. So that was easy. And if I want the voltage across the second resistor, V2, again, it's Ohm's law, I2R, what am I doing? It's I2 times R2 for the second resistor. That's now, let's see, we got 1 amp again times a new resistance, 4 ohms. So that's 4 volts. So 2 volts went across the first resistor, R1, 4 volts across the second resistor, R2. You notice that if I add that together, I get 6 volts, which is the battery resistor. So indeed, it was shared unequally because the resistors were unequal between the two resistors. Let's see, last part of the problem wants the power dissipated by each resistor. Well, the power dissipated by a resistor, we met that last class. You can obtain the power, figure the power by just multiplying the current through the resistor by the voltage across the resistor. It was that equation IV. In this case, for the power through the first resistor, it's I1V1. I won't write out the numbers to save some time here, but it's I1 is, where's I1? 1 amp. V1 is 2 volts, so it's 1 amp times 2 volts, so that's going to be 2 watts. And then for the second resistor, the power dissipated in the second resistor, P2, again, same formula, is the current through the resistor, that's I2, that's 1 amp, times the voltage across that second resistor. It's actually larger, it's 4 volts, not 2 volts, so I've got 1 amp times 4 volts, that's going to be 4 watts. So not only does the second resistor with the greater resistance have a greater share of the voltage, the second resistor with the greater resistance dissipates more power. It's turning more electrical energy into heat energy. Okay. Just to show you an example, here is a series circuit. So this is a 2 resistor series circuit. I've got 120 volts coming from a power supply down here. I got regular old incandescent light bulbs here. The power on the red lead and the black lead here that comes in, the electrical current that comes in and goes out, is fed up this arm, this yellow arm over here on the right hand side, it runs across this light tree here in the path that is connected. So I've got a lamp here and I've got a lamp here that are making connections here and here. So the current is flowing through these two lamps and then back down this arm over here. I've got to be really careful, this is 120 volts, not to touch. I'm always tempted to touch these things, but I must not touch these. But we see a 2 resistor circuit. And actually, we arranged that this bulb and this bulb have different they have different resistances, so that they have different fractions of the voltage across them, just like our R1 and R2, and so that they dissipate different amounts of power. And as you can see it, this one's brighter and this one's not as bright. So this one's dissipating more power. This one has a greater share of the voltage. This one has a larger resistance. Okay. This is just to show you. Yes. Oh yeah, thank you. This is just to show you, we looked at the water battery as an analogy for the electric battery. Here's the water analogy for a resistor circuit, 2 resistor circuit. In this case, the water is the electrical current. The waterfall, the entire waterfall, is the voltage supplied to this water circuit. And these individual steps are like individual resistors. So the same water current goes through all these individual water resistors that are in series, but each resistor gets a fraction, gets a share of the gravitational potential energy difference from the top of the waterfall to the bottom of the waterfall. So some of that gravitational potential energy difference is across this first step, some across the second step, some across the next step, so on, and the total adds up to the total gravitational potential energy difference. So it's sharing the gravitational potential energy across the different steps, but all the current, all the water current, is flowing through the different steps. So it is a nice analogy. Okay, let's move on. Resistors in parallel, that's the other basic arrangement. And so let's talk about the same things but resistors in parallel. See if we can do that. Okay, so, and I'll try and go a bit faster on this one because it parallels a lot of what we did for the series resistors. So we've got 2 circuits upstairs here to show us a parallel arrangement and the equivalent resistor for a parallel arrangement. So what we mean by resistors in parallel is indicated here. Here's R1, here's R2. They're connected up in this particular way to this battery supplying some terminal voltage. And if you look at this arrangement, if you walk around this circuit, if you're an electron going around this circuit, if you're the current flowing around this circuit, well, if you're an electron, you're either going to go this path here through the lower resistor, or you're going to go this path here. You don't go through both resistors, and that's what we mean by a parallel circuit. So this is a parallel arrangement, and then over here on the right-hand side, I've got a equivalent circuit, meaning that it contains one resistor, the concept of equivalent resistance. That for the same voltage, so for the same battery connected to the 2 circuits, would draw the same current, dissipate the same power as this pair of parallel resistors. So this is a definition of equivalent resistance for this particular arrangement. Again, I'm going to go through what are the keys to understanding this circuit, the parallel circuit. That's related to what happens to the currents and what happens to the voltages that are supplied by the battery. And I'm also going to go through what is the equation for the equivalent resistor. How do we figure out the equivalent resistor, which is a useful calculational tool. We saw that in the last example. So let's do those two things. These are the keys. If you remember for the series circuit, every component, every resistor in the series circuit got the same current, but they shared the voltage. The reverse is true here. Every resistor in the parallel circuit gets the same voltage. It's the voltage that's supplied by the battery. Every resistor in the parallel circuit gets some fraction of the electrical current that's supplied by the battery. And so I've described that here. Look, the voltage across the equivalent resistor, the voltage across R1 in this circuit, R2 in the left-hand circuit, they're all the same. They all get the full voltage that's being supplied by the battery. You can see that because the resistors, the terminals on the resistors just connect to the terminals on the battery. However, the current that's flowing out of the battery over here on the left-hand side, that current, I called it I, a fraction of it is going through the upper resistor R1. The remaining fraction is going through the lower resistor R2. So I1 is a fraction of I. I2 is a fraction of I. If you add together the two currents through these two resistors, I1 and I2, that is the total current that's being supplied by the battery. And so that's kind of how the current works in a parallel circuit. Based on that understanding, and again, just Ohm's law, that understanding with Ohm's law allows you to figure out for a parallel circuit what the value of the equivalent resistor is in terms of the individual resistors in the parallel circuit. I'm not showing you how to work that out, but it is simply that understanding about currents and voltages and Ohm's law. The rule is, upstairs here on the left and also upstairs here on the right, for the series circuit, the equivalent resistor was the sum of the individual resistors. For the parallel circuit, the reciprocal of the equivalent resistor, so 1 over the equivalent resistor, actually is the sum of the reciprocals 1 over these individual resistors. So in our case on the left-hand side, 1 over the equivalent resistor is 1 over R1 plus 1 over R2. And so that's the formula. That's the equation that describes the equivalent resistor for this circuit here. And again, that applies if you have 3 resistors in series, parallel. If you have 4 resistors in parallel, the same idea applies. The equivalent resistor for 3 resistors is 1 over R1 plus 1 over R2 plus 1 over R3 will give you 1 over the equivalent resistor, and so on for 4, 5, 6, whatever number of resistors you happen to have. There's an interesting thing about this. When you put resistors together in series, you make a bigger resistance. So you're increasing kind of the impedance or the resistance to the flow of the current. When you put resistors together in parallel, because there's this kind of reciprocal addition, this 1 over the resistance addition, you actually make a smaller resistance. What that's saying is when you put resistors in parallel to one another, look, you're making the current, you're giving the current an easier path from one terminal of the battery back to the other terminal of the battery, because it can flow through one resistor or some of it can flow through the other resistor. That makes the path easier, and so that means a smaller resistance for the equivalent resistor than any of the individual resistors, and that's what the mathematics of adding the reciprocals gives you. Okay, let's look at an example of this calculation. So here's a simple arrangement involving 2 parallel resistors. Again, it's actually the same components as the last problem. I've just arranged them in parallel rather than in series. So I've got 2 ohm resistor, 4 ohm resistor. They're connected across the terminals of this 6-volt battery in this parallel arrangement. Got the same question again. What's the current through the resistors? What's the the voltage across the resistors, and what's the power that's dissipated through the resistors. So I'm again going to work out all these quantities. There's 6 quantities there, and so again, we might first think that's going to take me a while, but we're able to do it pretty quickly using our understanding of the parallel arrangement and using Ohm's law. So let's see if we can go ahead and do this. Here we are. Oh, no. You're about to remind me, I can tell. Now I can just experience that reminder coming along. But what am I doing? Now I'm getting confused. Let me put that back. Let me document camera. Here we are. So I got ready to solve this problem. I drew the circuit out. Here it is, 6 volts with these 2 resistors. I'll call them R1 and R2 again in parallel. And I drew the equivalent circuit with a single equivalent resistor. I even calculated what it was. I'll call it R equivalent again. Remember, to find the equivalent resistance, you add the reciprocals of the individual resistances. So if I've got a 2 ohm and a 4 ohm, I'm going to add 1 over 2 plus 1 over 4, which is 2 over 4 plus 1 over 4, which is 3 over 4. That's the equivalent inverse, the reciprocal of the equivalent resistance. So I've got to turn it upside down. I'm going to get 4 over 3 ohms being the value of the equivalent resistance. And so that's my 4 over 3 ohms here. Now we can go ahead and figure out the current, the voltage, the power that's dissipated by each of these 2 resistors. Last problem we started by thinking about the current for the parallel resistors, and that was because for the series resistors, that's because the same current went through all the resistors. This time, I'm actually, although the question says current first, I'm going to solve potential first. That's the smart thing to do here. I'm solving potential first because the 2 resistors and the equivalent resistor all have the same potential across them. Actually, this bit, super easy. The voltage across resistor number 1 is going to be the same as the voltage across resistor number 2, because parallel arrangement. It's the same as the voltage across the equivalent resistor. I'll just call that R. And that's just the voltage that's supplied by the battery. So look, in that one shot, that key idea that they all have the same voltage applied to them, I've worked out that there's 6 volts across R1, there's 6 volts across R2, and that's the same as the voltage across the equivalent resistor. Now we can go ahead and calculate the currents. The current through R1, we can get that with Ohm's law. So it would be the voltage across the resistor R1 divided by its resistance. So that's just the 6 volts divided by the 2 ohms, and that will be 3 amps. And then we can do the same thing for the other resistor. The current through I2, that's by Ohm's law, is the voltage across I2, that's V2, divided by its resistance. This voltage is still 6 volts. The resistance is now larger. This has a 4 ohm resistance. And so we've got 6 over 4, that's 1.5. That's 1.5 amps. And so those are the 2 currents. And then finally, if we want the powers, well, now we know the voltages and the currents through the 2 resistors. If we want the power, we can use that equation, current times voltage. We keep using that for power. This case for resistor number 1, the power P1 is going to be I1 V1. I can just fill in I1, it was 3 amps. And I can fill in V1, it was 6 volts. And 3 times 6, 18 watts, joules per second. And I can do the same thing for the second resistor. It'd be P2 will be the power in the second resistor. It'll be I2 V2, the product of the current and the voltage for the second resistor. The voltage is still 6 volts. The current is now just 1.5 amps because the resistance was larger. And I won't write out the numbers, but 1.5 times 6 is 9. This will be 9 watts. And so there we are. We've walked around the entire circuit, figuring out all the interesting things about the components of the circuit, the powers, the currents, the voltages, and we used our understanding of parallel circuits to achieve that. Look, you've even trained me. I'm like a dog, or I'm like, what's that? Pavlov's dogs or something. I'm now trained to do it. So that's. I want my little treat now. Okay. Here's the water analogy for the parallel arrangement. So in the water analogy for the parallel arrangement, I've got a river. Here it is coming in, say, in the top right and entering on the bottom right. And look, there's this region where the river is split in two by this little island here. So some of the water is flowing around on the left-hand side of the island, some on the right-hand side of the island. This is a water equivalent of our parallel circuit. So the flow of water is like the flow of the electrons around the circuit. Some of the water current, like some of the electron current, goes around this path in a parallel circuit. The remaining goes around this path in the parallel circuit. So they're sharing the current of water like resistors share the current of electricity. However, as the water heads downstream, right, it's heading downstream because it's actually decreasing its elevation, its height above sea level. It's giving up gravitational potential energy. The water that flows the left-hand path and the water that flows the right-hand path fall down by the same amount of gravitational potential. Same amount of gravitational potential energy. And so they share the current, the two paths, but the potential drop between upstairs here and downstairs here is the same for both the left-hand and the right-hand path, just like the voltage drop in a circuit. Okay. Let's move on. I think I'm going to look at some more examples, illustrations of electrical circuits now. And as I say, what we're going to start now will carry on getting ever more, you'd be pleased to know, ever more sophisticated or complicated in this class and the next class. So we're going to deal with some more sophisticated circuits. Oh, but I've got a quiz question first. So in this quiz question, we're asked to think about two electrical circuits. There's one on the left and one on the right. The one on the left is circuit A, it's the parallel circuit. The one on the right is circuit B, it's the series circuit. And we're asked in which circuit we're asked to compare the power dissipated in the two circuits. We're asked to compare the power dissipated in the two lamps, which are two resistors in the two circuits. Which circuit, A on the left or B on the right, dissipates more power, or do they happen to they're made out of the same components, dissipate the same amount of power? So I'll give you a couple more minutes to think about that, chat about that, reminisce about that, and then we'll move on. Okay, maybe I'll move on. Let's just go through the answer to this problem. We've got a parallel circuit on the left-hand side. We've got a series circuit that's on the right-hand side. The parallel circuit is connected to a battery. The series circuit is connected to an identical battery. We've got to compare the power that's dissipated in the parallel arrangement and the series arrangement. Let me demonstrate it. So I'll actually make the parallel and the series arrangement. So actually here, this is the series arrangement. So I'm going to switch this back on. Okay, I'm up to 120 volts. This is the parallel arrangement. I've got a current, an electrical current, that's coming up this arm over here on the right, and the single path that current can flow is across this horizontal arm here and down back through this left-hand arm. On the way it passes through this resistor, a lamp, and this resistor, another lamp, and this is a series arrangement. And you can see the power that's being dissipated. You can visualize the power that's dissipated just by the brightness of the lamps, because the lamps are turning electrical power, they turn it into light energy, and also some heat energy, but you can see the light energy. So just try and remember how bright or how dim this series arrangement is. And now I'm going to turn it into a parallel arrangement. As I do this, my hand will be shaking mildly in case I touch something. So I've arranged these two now in parallel. Okay, the current could come up over here on the right-hand side, and now it's got two options. It can go across this horizontal path or this horizontal path, but at the moment I don't have a circuit. So I've got this little piece here I can shove in. Okay, so now I made it into a parallel circuit. So remember back to when you saw the series circuit, I think this looks way brighter. These lamps are way brighter. They're dissipating much more power. They're turning much more electrical energy light energy and heat energy. So it's clear as a practical point that the parallel arrangement over here dissipates more power. The series arrangement less power. And you can even see it in the picture, right, on the screen. The parallel arrangement, you can actually see the bulbs are lit. The series arrangement is hard to see. You can barely see the bulbs are lit. Why is that? Well, in this case, the parallel arrangement, the resistors or the bulbs are getting the full voltage that's supplied by the battery. So if they get the full voltage that's supplied by the battery, then they'll each have larger currents because they have greater voltages. They get larger currents by Ohm's law. And if they have larger currents and larger voltages, they're going to dissipate more power. So that's one way of thinking about it. When you have a series circuit, each of the individual resistors shares some of the voltage. It's got less voltage. It's got less voltage across a resistor. It's going to have less current through the resistor. And so again, the product of current and voltage is going to be much smaller in that case. And so you're going to dissipate less power. Okay. I want to come back to the real battery and just look at another example that involves the real battery. So in this overhead here, we've been given a circuit involving a real life battery and a single resistor. This guy down here. There's a little bit of language we sometimes use here. This would be called the load resistor. It's the circuit that we're powering with the battery. It's called the load resistor. So in this particular problem, we're told that this real battery's EMF, its EMF is 15 volts. But its terminal voltage, what we're getting out of the battery, is actually less than that. It's 11.6 volts. It's 11.6 volts when we deliver 20 watts of power to this load resistor. And we've got to figure out what the load resistor is, and we've also got to figure out what's called the internal resistance of the battery is. So let me start by explaining our picture, our model of a real battery. It's in this box here. The way we visualize a real battery, as opposed to a perfect battery, ideal battery, is that a real battery has both a source of electromotive force, an EMF, but it also has what's called an internal resistance in series with that EMF. An ideal battery is just a source of EMF, but it has no internal resistance. So a real battery adds the internal resistance. That's what you see here in the box. So the box is the battery. The two terminals of the battery are over here on the left and over here on the right. That's the voltage that's coming out of the battery. That's the terminal voltage of the battery. Inside the battery is this little bit of magic or model that is a EMF, which is fixed, and a internal resistance, which is also fixed. But the way it works is the more current you draw from the real battery, the more current we draw, the more voltage we drop, the more voltage across the internal resistance. That means that the less voltage that's available to the remainder of the circuit, to the load resistance. And so that's how we model a real battery. And really, our understanding of the real battery in this circuit is based on our understanding of resistors in series. In this circuit here, instead of having R1 and R2 in series with the battery. I've really just redrawn it of having a EMF with an internal resistance to the battery and a load resistance external to the battery in series with one another. So you can think of this as the battery R1, R2 series circuit. I've just relabeled things as internal resistance and as a load resistance. And so as you draw current through the load resistance, as current flows around the circuit here, some of this 15-volt EMF is lost to you, is dropped, we call it dropped across the internal resistance. So we're told in this problem, right, that the battery's EMF is 15 volts inside this box, but its terminal voltage between here and here on the left and right, or the terminal voltage across the load resistor here, that's only 11.6 volts. It's 11.6 volts when we're dissipating 20 watts of power in this resistor. We've got to use that information to figure out what, it's not R1 and R2, but what the load resistor is and what the internal resistor is. So let's see if we can do that. Quite proud of myself now. Okay, forgetting what I'm doing. I'm going to solve this problem. We want to solve in this problem, which I've depicted here, right? I've drawn the circuit. I've redrawn the circuit. I've indicated the things I know. The EMF of the battery, 15 volts. The voltage across the load resistor, 11.6 volts. The load resistor is dissipating 20 watts of power. So I've labeled the quantities that I know, and I want to figure out what the internal resistance is here, the little r, and what the load resistance is here, big R. The way I'm going to solve this, the key thing that I want to find out, before I start asking the question, what's little r, what's big R, I'm going to figure out what's the current that's flowing around this circuit. The current that's flowing around this circuit is kind of the unifying thing because it's flowing through all the components of the circuit. So I want to figure out the current that's flowing through the circuit. I'm going to call that kind of part A. And I'm going to figure out the current that's flowing through the circuit by thinking about the power that's dissipated in the load resistor. That power that's dissipated in the load resistor is the current through the circuit. I'm just going to call it I because it goes through every component, multiplied by the voltage across the load resistor. Same old equation for power again and again and again. Keep using it. All I need to do to find the current is rearrange this. I will be the power in the load resistor divided by the voltage across the load resistor. That's 20 watt divided by 11.6 volts, and I already figured that out. That's 1.72 amps. So that was easy. That was straightforward. If we thought about that question, right, the key was to think about that question. What's the current through the entire circuit? Current that's flowing through the battery, current that's flowing through the internal resistance of the battery, the current that's flowing through the load resistor in the circuit. We can figure that out knowing the power through the power dissipated by the load resistor and the voltage across the load resistor. Now it makes it easy to figure out what R, little r, what did I do? Crap. I've changed the mode of this. I've come back.
Part A, resistor rate 20 watts.
Say that again.
In part A, resistor rate 20 watts.
Yeah, well, that's my 20. Yeah, you're absolutely right. I'm surprised anybody can read any of the numbers that I write, to be honest with you. They're some sort of ancient Gothic writing that I've inherited. So little r, what's the resistance little r? We can figure that out, the resistance of the internal resistor, now just by Ohm's law. Ohm's law applied to little r tells us that the, actually let me do big R first. I think it'd be clearer. Same idea though. We can just apply Ohm's law to the load resistance, big R. We can figure out the load resistance, big R, just by Ohm's law, so it would be V equals IR. So V, that's the voltage across the load resistor, divided by the current through the load resistor, which is the current through everything. We know both these quantities. This is 11.6 volts divided by, what's the current? 1.72 amps. That comes out to be 6.7 ohms. So that's the resistance of the load resistor. We want the resistance also of the internal resistor. So that's going to be the voltage across the internal resistance. I'll write that V subscript little r divided by the current, same current again. We've got to divide the voltage across the internal resistance by the current. What is the voltage across the internal resistance? Well, it's the remainder of the 15 volt EMF. So the EMF is supplying 15 volts. 11.6 of it went to the load resistor. The remainder is what is across the internal resistance. So this is actually going to be 15 minus 11.6 divided by 1.72 amps. 15 minus 11.6, what's that? That's going to be 3.4. I'm trying to correct my, it looks like a 16. But either way, nobody's going to read it. 15 minus 11.6 is 3.4. 3.4 divided by 1.7 is 2, basically, is 2.0 amps, ohms. And so that's the internal resistance. And so that's another circuit problem. It allowed us to revisit the real-life battery compared to an ideal battery. But we understood it as a series circuit involving resistors. Any questions on that one? I just thought I'd show. Actually, I wanted to show this, and then look at one more example. This slide has two formulas that are kind of handy sometimes. They describe the real-life battery. They describe upstairs is the terminal voltage from the real-life battery. They describe downstairs here the current that's supplied by the real-life battery. In terms of the internal resistance of the real-life battery, they're just based on using Ohm's law. They're sometimes handy. This one up here says that the terminal voltage is going to be smaller than the EMF by an amount that depends on the current that you draw. So the more current you draw, the smaller the voltage of the terminal voltage of the battery, which is how we started off the lecture class, talking about that. Also, the current that you draw from that battery is less than the current you would expect based on the load resistance. It's more. The current is less. The resistance is more because there's the internal resistance that the current also has to flow through. So sometimes these two equations are useful. Okay, I want to get on to the last topic here. which, as I say, we're going to continue in the next class, and that's more complicated circuits. Here's an example of a more complicated circuit. If you look at this circuit here, it contains a battery, it contains a bunch of resistors. It's not simply a parallel arrangement or a series arrangement. It's a more complicated arrangement of resistors. So how on earth will we go about solving this problem? Okay. Here I am in therapy for many years now, and we're trying to solve this problem of electrical circuits. How are we going to go about solving this complicated problem of that electrical circuit? It's like a complicated mind, has all these things in it, they're all sort of jumbled up. That circuit looks like something that is jumbled up. How can we ever go about it? There is a procedure for doing it. So the procedure for doing it, when you have a complicated circuit with many resistors in a complicated arrangement, is to look into the circuit and to find some piece or part, or component of the circuit which just looks like either resistors in series or looks like resistors in parallel. It looks like a pure series or pure parallel circuit. When you find that part that looks like it's pure parallel or is pure series, then you're going to replace those components with a single equivalent resistor. So maybe you found a part where there's two parallel resistors. You're going to replace that with a single equivalent resistor. Or maybe you found a part of the circuit where there's two series resistors. You're going to replace that with one equivalent resistor. You've made the circuit just a little bit simpler. Then you do the same thing again. You've got a new circuit now. You're going to look back into it, and you're going to look around in it, walk around in it, and find another place where you can see that there's an arrangement of resistors which is simply a series arrangement or simply a parallel arrangement. And if you find that series arrangement, you're going to replace it by equivalent resistor. If you find the parallel arrangement, you're going to replace it again with another equivalent resistor. That's a procedure, that's a method that you can keep doing over and over again. And if you do it over and over again, eventually you get yourself to the point where you've just got one single equivalent resistor that represented the entire circuit. Once you've got that one equivalent resistor that represents the entire circuit, then, for example, you can figure out, if it's connected to a battery, how much current that battery is supplying. And once you've got how much current the battery is supplying, how much voltage the battery is supplying, then you can figure out just with Ohm's law how that current and voltage is shared across all the components of all the different components of the circuit. So this is setting up a problem. Let me go back. This one here, and the procedure for solving this problem. And we're going to look at that problem in the next class and other problems in the next class where you have more complicated arrangements than just parallel or series circuits. So just to remind you what we did today, we talked a bit about ideal batteries and real batteries, how we model real batteries as an EMF and internal resistance. We talked about resistors in series and the keys to understanding that. The current goes through all of the series components. We talked about resistors in parallel, the key to understanding that. The voltage is across all the components. And we looked at sample problems. We looked at sample problems with resistors in parallel, sample problems with resistors in series. I'll hang out here if you've got any questions.
That's one of the three. I can narrow it down. There's way too much to not have enough.
Thank you.
Sure. See ya. Yeah.
Whenever you like draw the circuit, why is it flowing from positive to negative when the electrons are flowing?
You mean
Like
on the battery?
In some of the slides, the arrows point out of the plus, like in the direction.
Oh,
of 2
yeah. So the current is always drawn in the direction that positive charges would move. So this is the confusing thing, the mistake that made that was made before they knew that there's electrons going round and the electrons were negative. So when we draw current, we always draw it in the direction that a positive charge would move.
Yeah.
Although it's in metals, it's electrons that are going around and they're going in the opposite direction.
Yeah.
So that's
Okay.
Yeah.
Thank you.
So for the test, the 3 homework worked out problems, is homework 1 content free game, or is it just the homework 2, 3,